Welcome back. In this video, we're going to be going through some examples relating to our couple forces, as well as distributed loads and centroids. So we're going to start with this first question here, which talks about force couples. So we want to find the resulting couple moment to be 12 kilonewton meters. So that we're working backwards, so that wants us to find F. So in this case, remember, we only need the distance between two. So let's start with our 8 kilonewtons. And the distance between them, we want our vertical distance, which is 1.2 meters. So I'll draw this schematic again, 1.2 meters, it's 8 kilonewtons. If we connected them, that would go in a counterclockwise direction. Now let's split our F into X and Y components. So what we're going to do for that, we're going to do downward and upward component. So this is our downward component is F cos 30. And the distance between them is that 0.4? No, this is 0.3 between them. And for our X components, since they are not separated by a vertical distance, since they both originate from the same spot, then we don't have to worry about that. So then if we follow this is also counterclockwise. So we know that our moment is equal to 12 kilonewton meters. So we want to find what F is. So this is F cos 30 with a distance of 0.3 meters, and that's plus our 8 kilonewton couple. That's 8 times 1.2 meters. And so then this, we can move this to the other side. So as we simplify this, so then this is this is 12 equals 8 times 1.2. That's 9.6. Plus our F cos 30 times 0.3. So then let's move this 9.6 over. This is 1.25 equals F cos 30 times 0.3. Let's move that 0.3 over, so divided by cos 30 times 0.3. And this is going to give 4.811 kilonewtons equals F. Okay, it appears I have made a mistake somewhere along the line, so let me just check back with my work. Sorry, this is meant to be subtracted, not divided. I apologize. So then that's 12 minus 9.6, so that's 2.4. And then when we divide by cos 30 times 0.3, there we go, that is our answer. So then F is equal to 9.24 kilonewtons. Okay, our next question, we want to replace our loading system with an equivalent resultant force and moment at point O. So how would we do that? So from this system, we want to find the Cartesian formula for each of our forces. And then we want to find our resultant. And then our resultant moment. So let's start with our F1. F1 is, so our magnitude is 100. And if we wanted to take our unit vector, actually let's start with our position vector first. So it originates from this point out. So if we start with F1, sorry, I've got my bearings again, we can see that it is in, so this is our y-axis. So we see that it is in our negative j direction, negative y direction. And let's say this is our positive x direction. For F2, oh sorry, we'll start with F2 first. So sorry, coming back to this now. I'm going to start with this moment directed here, so this is MC, and let's say this is our negative I direction, so this is our x-axis here, so then this would be negative 75 I direction, and lastly, for F2, sorry, the image got cut off here, this measurement right here is, so this is 0.4, and our height is 0.3, so if we were to redraw this, we can look for this angle here, so 0.4, 0.3. So we can just use sine ratios. So sine, this is 0.5, right? Because this is kind of like our 3, 4, 5 one, just with moved over a decimal place. So if we wanted our x, this is 0.4 over 0.5, and our cos ratio, which is our y, is 0.3, 0.5. So this is going to be respective to our direction for that. So then this is negative, so that is along our negative I axis, so that's 0.4, 0.5 I, and this is directed downwards in our k direction, so it's minus 0.3, 0.5 k. All right, so if we added up these forces, our resultant, oh sorry, this is times our magnitude of 200, so then this is equal to, so 200 times 0.4 divided by 0.5, so this is negative 160 I minus, that's 200 times 0.3 divided by 0.5 minus 120 K. And then when we get our resultant force, this gives negative 160 I minus 100 J minus 120 K. That's what we have for answer up here. So that is our first part. And now we want to find our moment, our resultant moment about point O. So what we can do for that, we want to split up our, so this is part 3 moment. So we need to split up our forces again and just consider them individually. And we want each of their distances from the point we're measuring at, which is our origin. So we need our OA, so that position vector there, and we need this distance, our OB. So then our resultant at point O is going to be our OA cross our F1, and F1 is in a counterclockwise. And then we're going to add our ROB position vector times F2 force, as well as our moment MC that was given over here. So let's do just that. I think we might be squishing our work a little. So point A is 0.3 positive, and then B, so this is 0.5. So then that's 0.5 in our positive y direction. This is at a height of 0.3, and that is 0 up at the top, because we are not moving that way at all. And this acts as a free couple, so it doesn't really matter where the location is. So, given that knowledge, so we'll have I, J, K, then our OA is just 0.3 K, then our F1 is negative 100 J, then for our second one, this is 0.5 and 0.3. And we have negative 160I, 0, and negative 120K. And then this will give us, so I'm not going to do the math, I'll let you guys do this on your own just so you can have that practice. And this should give you negative 105I minus 48J plus 80K. Okay, so I'll have you try that on your own so you can get some more experience with using cross product. Okay, this next problem is talking about distributed loads, so we have to use our knowledge of how to use distributed loads in order to solve this problem. So let's divide this into two triangles. So we have this one here, and then our other one, which I'm going to highlight in yellow. And we want to find our magnitude of our resultant force. So our resultant force from our first triangle is going to be acting somewhere here, close to the thicker end, and then our next one is going to be acting somewhere around here. I'll draw that so you can see it better. So let's find where those loads lie and what their quantity is. So let's start with our red triangle. So it spans a length of 7.5 meters, and it has a height of 6 kilonewtons. So then our force from that is the area of our triangle, so that's base times height, half, so that's 7.5 times 6 divided by 2, and this is 22.5, so let's write that 22.5. And then for our second triangle, this is going to be, so it's 6 in height again, we have 4.5 base, so then for our second one, this is 4.5 times 6 times half, 4.5 times 6 divided by 2 is 13.5 kilonewtons. And let's find where these forces are going to act. So it's going to act 1/3 of the length away from the thickest part of the triangle. So then if we had 7.5 divided by 3, so if we divided it into thirds, each one would be 2.5 meters in length. So that means we have to get one section and then two sections of our 2.5s to get that distance from point O, because we want to measure it from point O. So then this gives us a distance of our new force, our equivalent force, of 5 meters. Now we can do that with our other one. So if our total distance is, actually no, let's do the same thing. Let's divide our sections into thirds. So 4.5 divided by 3, each one is worth 1.5. So if our total length of our beam is 7.5 plus 4.5, so if our total length is 12 meters, then we want to find what 12 is, and we want to subtract these two sections to get where it's applied here. So then that's 12 minus 1.5 minus 1.5, and that is 9. So this is 9 meters. Sorry, it's a bit messy. So I'm going to say at 9 meters, and this one is at 5 meters. So if we were to redraw all of this with our equivalent loads now, we'd find that this acts here. It's 2 and 2.5, 5 meters. And we have at 9 meters, this is 13.5. So if we add all of our forces together, we only have them in the y direction. So then this is equal to negative 22.5 minus 13.5 minus 15. And this is negative 51 kilonewtons in our downward direction. And we want to know where this is acting. So we're going to start by finding our resultant moment. And we're going to take each one separately. So we're going to start with our free moment here. So this is counterclockwise, so it's minus 500. Then we have our 22.5 force. So that's our equivalent force. That's a distance of 5 meters from point O. And if we were to get to point O, we would have to go in a clockwise direction, so that is also negative. And this is minus 13.5, and our distance is 9 meters. And then we have minus 15, and the whole length of our beam is 12 meters, and that will give us our moment. So let's do some math. That's 500, 2.5 times 5, 13.5 times 9, plus 15 times 12. It's going to give minus 914 kilonewtons per meter. So that's all we need for this question because it doesn't really ask us for anything else. You can also express this just as its magnitude and then add its direction, which is what the answer is done, and it's negative, so that means it's in a clockwise direction of rotation. If we want to find where it's being loaded to, we know that our moment is equal to our force times our distance. So if we want to find that, what we can do is we can have our magnitude of our moment equal to our magnitude of our force times some distance L. And so when we take 914 divided by 51, I think this is wrong, hold on. Okay, so I'm not too sure how to work with this one right now, so I want you to just ignore what I just did and just take our final answers, our resultant force and our resulting moment about point O from our forces. Okay, and we got 2 more questions left, so let's work with problem 4. So we want to replace this loading system by an equivalent resultant force acting at point B. So what we can do, since we have a trapezoid in this one, we have to divide it into 2 sections. We have a triangular region and a rectangular region for the angled part. So we can start with this one. So we have 750 spanning a distance of 1.2 meters. So that's 1.2 times 750. And that's 900 newtons at a distance of 1.2 divided by 2. And this is 0.6 meters. All right, so if we started with our triangle, I'm actually going to break this up into a different way. So there's an equation we can use for when we have trapezoid forces. All right, it appears I cannot find that equation, so it looks like we are going to be going with the old-fashioned method, where we use a triangular section and a rectangular section. So for the rectangular portion, I'm going to use blue. So that's going to be acting in the center, and that is our height of, so we need this new height now, so that will be that's going to be 750 in our height, so that is 750 times our length, so this is 750 times 1.8, and this is 1350 newtons at a distance of, so that's 1.8 divided by 2, 0.9. And now for our triangular section, we want this height here, so then we do 1500 minus 750, and this is just 750, and it's going to act at 1/3. So if we take the area, so that's 750 our height times 1.8 our base divided by 2, this is 675 newtons at a distance of, so that's 1.8 divided by 3, that's 0.6 meters. Okay, so to solve this question, we're going to need to break it out into our different x and y components. So let's do just that. So then our F1, so that's just our 900. This in our y direction, that's just 900 and negative. So then if we were to use, let's call this red one F2. So this is, let's clean that up a bit. So in our x direction, we have a positive x direction. So that's 675. And then the angle between our beam and our horizontal is 60 degrees. So this is acting 90 degrees. So the angle between our vector and the horizontal is 30 degrees. So this right here is 30. So that 30 degrees is opposite, no, is adjacent, so this is cos 30. Then F2y, since it's pointing downwards, that's negative 675 sine 30. Same thing goes for our F3 in blue. So this is 1350 cos 30, same angle. And this is negative 1350 sine 30. Okay. So then when we find our resultant, this is equal to, so take our x components and add them, so that's 675 cos 30 plus 1315 cos 30, and that's equal to 170.53.70 I minus 1912.50 in our j direction. And now to find our resultant moment at B, we can use each of our position vectors like we did previously and use it to get to that point B. Okay, sorry, I'm trying to figure out how I'm going to do this. Okay, so let's start with our 900 newtons. So we're going to keep this in Cartesian form. So then if we start with our 900, that's from our B2 there, that's negative x direction, so that's negative 0.6 I times 900j in our negative direction. And then we're going to use our x and y components. So we had negative 675 sine 30, and our distance is, so if we had it like that, we'd want the horizontal distance to be from there. So then this would be, okay, so if this was acting at 0.6, that means our length here, so if we drew a triangle here, so imagine we just drew the triangle, I just translated over here, so that's 1.8 minus 0.6, so that's 1.2 meters. Our angle is 60, so we want to find our horizontal distance for our vertical component and then add it to this horizontal distance here. So this is, cos 60 is equal to x over 1.2. So that's cos 60 times 1.2. So this is 0.6 in our x horizontal. And then while we're here, let's solve for the vertical distance, which is equal to sine 60 equals x over 1.2. Sine 60 times 1.2, and that's 1.0392 meters. So we're going to solve separately for our x and our y components. And this is in our negative j direction. And this is multiplied by 0.6 plus our 1.2, 0.6 plus 1.2, and that's a horizontal distance of 1.8, and we started from B to go there, so then that is in our negative I direction, plus 675 cos 30, so this is our x component now, in our positive I direction, and we want our vertical distance that we'd have to travel to be in line, which is 1.0392 negative j. And this is plus 1350 cos 30, and then the separation distance. So if we were to draw a triangle like this, for blue, half of 1.8 meters is 0.9. We have 60, so sine 60 times 0.9 is 0.7794, and 0.9 times cos 60 is 0.45. So if we use our downward, no, sorry, this is, we want to use our, sorry, this is a mistake. So if we start with our x component first, this is in our positive I direction, and this is multiplied by 0.45 plus 1.2, so 0.45 plus 1.2, and that's in our negative I direction. Oh, sorry, no, we wanted our vertical, and that's negative 0.794 j. And this is plus our last one, so that's 1350 negative j direction. And then times our horizontal distance, which is 1.65 in our negative I direction. Okay, so once we add these all up, so it's not quite our answer, but the method still stands. This gives us I got a number a little bit bigger, so it's 3,967.924. And this is in our positive k-hat direction, because when we have positive I cross product positive j, that gives positive k, so we make both of them negative, that still makes k positive. And this is newtons per meter. Bit of a tough one, a lot to break down, and there's a lot to process because you have to keep all your distances in order. But yeah, that one wasn't too bad. Okay, so I'm going to leave this one for you guys to do on your own. This is the same method that we used for our previous example. Just you're going to be adding a new Z column and a new AZ area Z column, which means you're going to have a new center to find for your Z component, but the process remains the same. So just make sure you're wary of where each component lies. So just if I give a debrief, so if I were to start with this component, just know that the center of gravity in our y direction is going to be 1/3 of 1.5, so that's 1.5 divided by 3. So that's 0.5 distance here. And that's going to be plus our distance from our x-axis to our to that point. So that's 2, and then plus our 0.5, sorry, along our y-axis. So you just have to be aware of things like that. Otherwise, it's pretty much the same thing. Just make sure you're being really careful with your math. All right, so that brings us to the end of this video. Let me know if you have any questions, and I will see you on the next one.